Okay, so I can resume then for, as I say, I won't quite get through right to the end of velocity jump random walks today, but I mean, I should get sort of most of the way there actually, and then we'll kind of continue with that on Thursday. Just a kind of a final note on those kind of precision jump random walks with a control species. Part of the nice thing about that is it's very extendable, so you can incorporate other types of dependencies in there. And one example with that, if you wanted to include some sort of volume exclusion type effect. So an idea that kind of cells, you know, if you've kind of got a population of cells that you can only fit a certain maximum number of cells in a particular area, they can't occupy the same position in space. You know, you can incorporate that through this sort of process, and then you derive sort of modifications of that Keller-Siegel framework. But in other words, as I say, you know, it kind of allows you to kind of, you know, kind of incorporate various levels of microscopic scale detail and then work out what that kind of macroscopic model is going to look like. And again, there's kind of been various sort of extensions, and I'm happy to provide further references on this sort of area for anybody that's interested. Okay, so let's now go on to the next type of random walk that we're going to, and we're going to again stay in 1D. But whereas we've been looking at kind of uncorrelated random walks so far, we're now going to turn our attention to a correlated random walk, where basically you continue to move in the same direction. And we're going to consider a very simple one, which is being kind of well studied, where you suppose your particles move right or left with some speed s, and they switch their direction of movement with a turning rate mu over t. So this is kind of my picture in this sort of case here. I have my kind of, I have rightward moving particles, which I denote u plus, leftward moving particles u minus, both moving with speeds s, and they switch from one to the other with a rate mu over 2. So given that, let's denote u plus minus x of t as being my density of right and left moving particles at position xt. And for this type of process, you can write down what's called the Goldstein-Kac model for a correlated random walk. And it takes the form of these two equations here. We've got a coupled pair of hyperbolic equations. The first equation is describing the evolution of my rightward moving particles. They move right with some speed s, so we've got this advection term here. And then these right-hand side terms are just this kind of switching that at a kind of a rate mu over 2, you switch out of moving right. So you, and of course, you gain particles that were originally moving left. And then the same, effectively the same type of equation for S, but now of course we've got a change in the direction of movements. We've got a minus S there. And of course, these terms on the right-hand side are just sort of like, we've got switching of signs in there. Okay, so that's what we call the Goldstein-Kac model for this correlated random walk. And just as a kind of a further note, actually, this kind of right-hand side can also be kind of switched in this sort of, written in this sort of way here, which is another common way of writing this sort of process. So you sometimes see this Goldstein-Kac model written in this sort of form here, and other times you actually kind of see it written in this sort of form there, which is sort of two alternative forms. Okay, so that's the Goldstein-Kac model for correlated random walk, and we'd like to try and get a similar derivation of a macroscopic model, kind of for macroscopic variables. So to do that, we're going to define two macroscopic variables. We're going to describe the macroscopic density, which is just going to be the sum of my right and left moving particles. And we're also going to define what we call the macroscopic flux, which is basically my speed times the difference in these two particles. And this is akin to the kind of the macroscopic flux that we talk about in when we're kind of deriving those partial differential equation models from a kind of mass conservation type arguments. And the goal now is to try and get equations for these two macroscopic variables. So how can we do that? That's kind of my setup here. Well, it's actually some very straightforward calculations that we can do to get from one to the other. So let's kind of go through those. So here's my two equations up here. We start with those. And the first thing we do is just add those two equations together. So it's just a case of kind of looking through the u plus t plus the u minus t. When we've defined that macroscopic u as being u plus u minus, that's going to give me this u minus t. Again, maybe I should just kind of use my pen here just to kind of highlight this. Okay, so those two there will give me that one there. What about when I add these two up? Well, we've got plus su plus x minus su minus x. That just gives me a plus vx there. And then, of course, the right-hand side terms all cancel with each other out. So that's just going to be equal to 0. So adding those two there just gives me a very straightforward equation. I can do another type of manipulation. I can subtract equation 2 from equation 1 and then multiply through by the speed. And when I go through that, well, I get an equation which is now vt plus s squared ux is equal to minus mu times v. Okay, so these are very, very straightforward manipulations that we're doing. You can go through these yourself and convince yourself of these. Okay, so given 3 and 4, what do I do next? And sorry, before I go on that, I should just note that this kind of coupled systems here is what we refer to as a Cattaneo system. Well, the next step is to do a bit of simple differentiation. I differentiate the first equation, 3, with respect to t, and obviously I just get utt plus vxt is equal to 0. I differentiate the second equation with respect to x. I get vxt plus s squared uxx is equal to minus mu vx. And of course, minus mu vx, using this equation 3, I could rewrite that right-hand side as simply mu times ut. Okay. So that gives me these two equations there. But now, of course, actually, I can kind of couple these together because that first equation gives vxt is equal to minus utt. So I can combine those into a single equation, which is called the telegraph equation. And this was actually, of course, because it was actually described as a way to model the movement of telegraph systems across cables in the very early stages when people of kind of long distance communication through sending telegraph signals, basically. And that gives me this partial differential equation system here. Okay, so that's what we have called the telegraph equation. And again, we're going to consider a limiting scenario. And in this case, we consider a limiting scenario where we take the turning rate mu and the speed s to infinity in a way such that the limit of s squared over mu is equal to some diffusion coefficient d. Okay, so you do that, and you can kind of see, therefore, that because mu is going to infinity, that term's going to disappear. This term becomes a constant, and again, we recover a diffusion equation in that limiting scenario. Okay, so also from the perspective of a correlated random walk, we can obtain diffusion type equations. You can change this slightly to include a bias in your turning rates. So now let's actually kind of assume that we've got a bias in the turning rates. And can anybody tell me what they expect that we're going to get in the macroscopic limit in this case here? Well, let's go through the calculations in this case. I'll go through them fairly quickly because it's just the same set of steps. We now bias my turning so that we slightly more frequently turn from left to right, basically. So there's a slight bias towards the rightward direction in this case. We're more likely to turn from left to right than from right to left. So that's what we've set up here. So you go through the same sort of calculations. You add equations 1 and 2 together. You do s times 1 minus t. You're now going to get some extra terms appearing here because these right-hand sides don't kind of, don't quite sort of cancel each other out in quite the same sort of way. So you kind of get an extra term in there from this sort of process. You go through the same process of then differentiating equation 3 with respect to t and equation 4 with respect to x. You combine those together, but now you get an extra term appearing in there as well. So now, very much like when we were kind of talking about that kind of earlier uncorrelated random walk where you jumped right with probability q and left with probability 1 minus q, in order to kind of study the limiting equation from this, you need to think a little bit carefully about the limit, because we've now got potentially different size terms when we kind of do this. But you can describe various sort of limiting scenarios, and I won't go through them all because you can kind of you can do these yourself. If we take a limit in which mu and s tend to infinity and epsilon tends to 0, such that we kind of have the same limit of s squared over mu being equal to d, but now the limit of epsilon s is equal to c. So effectively, epsilon has to scale as 1 over s in this sort of limiting case. Then we obtain a diffusion advection equation. And that makes sense, as I say, because we've now introduced a bias into this sort of process. You're more likely to be in a rightward moving direction, and so therefore it's kind of that's kind of reflected then in the kind of the limiting equation that we obtain. And of course, you could consider other limits here. In this case here, where you have different, you have kind of according to the size of epsilon, etc. You're going to get different sort of limits. And as another exercise that you may want to try and go through yourselves to do, you could also try and see what happens if you consider a bias in the speeds instead. There's now 2 different ways for this correlated random walk where you could introduce your bias. You could introduce your bias in your turning rates. You could introduce your bias in your speeds. Do you get a similar equation when you do it the other way around? And again, I'm going to leave that there with something for those that are interested to try and investigate.
I have a question, if I may.
Mm-hmm.
So I would like to hear, please, a comment on the initial condition, because it seems that also depending on the scaling that you do, you will need more or less initial conditions, right? So
yeah, I mean so actually, yes, if you kind of, of course, you've now got 2 populations to start with, basically, yes. So, yeah.
But for instance, in the case of the telegraph equation, you will need a condition for the positions and the velocities, right?
Yeah, absolutely. Yeah.
Why?
Yeah. I mean, in this case here, there's just only 2 velocities, basically. But yes, of course, you would need to define an appropriate condition for both your populations. You may force your particles to be only moving rightwards from the start, basically. Yes.
While in the last case, like rescaling in the way that you propose, it seems that for the limiting equation you will need just the position. Is it correct?
Yeah, exactly. Because in that case, there you're not actually there's no actually kind of movement in a particular. You're simply jumping right or left. Exactly. So.
Okay.
Mm-hmm. Okay. Okay, so as I say, the correlated random walk, as I say, is another way then to sort of set things up. And again, this framework can be extended, and I won't kind of talk about these in more details than just simply providing some references and giving a bit of a sort of a context for this. Whoops. Okay, so whoops. Let's go back to that one there. So, for example, this kind of framework has been modeled by people like Hillen, Stevens, and various others there to actually explicitly model chemotaxis. So then you choose potentially speeds that vary with some concentration C. You have turning rates that can kind of change with the concentration C and or even the gradient of C, etc. So you can kind of set up those models to describe chemotaxis. And these models have also been used to kind of describe swarming type sort of behavior in populations as well, using kind of a non-local formulation similar to the kind of, somewhat related to the non-local models I was talking about yesterday, which kind of describe those kind of swarming sort of the properties of individuals and how they kind of interact with their with the other members of the population. But as I say, it's just to give some information. If you're interested in that extension to chemotaxis, the study of Hillen and Stevens is a good one to start with. It's one in swarming. This study of FTME and others is a good place to look at. Okay, so that kind of brings me then to the end of the 1D part of this. So let's summarize what we've got to so far. For the unbiased random walk, we showed that we could generate diffusion equations in the macroscopic limit, whether starting from this position jump or Goldstein-Kac random walk. With a biased random walk, we could generate advection diffusion equations in the macroscopic limit, but actually then whether or not the equation that you get is a pure drift process or something mixed or diffusion depends crucially on some of those individual parameters. You can incorporate control species dependency, and then you can obtain Keller-Siegel type equations, but then actually, the actual exact equation that you get really kind of depends quite precisely on what local rules have been imposed and so forth. And then, of course, you can also kind of do this either within a kind of an uncorrelated or correlated random walk type framework as well. Okay, so that's anyway where we're so far. But this has all been in one dimension, and of course, it's very rare in the biological world that the population that we're interested is confined to a one-dimensional line. There are instances where that's a valid approximation, but generally we're interested in either 2D or 3-dimensional processes. So how can we extend this up now to higher dimensions? So biological applications would typically require consideration in movement in 2D and above. And I'm going to talk about, as I say, for the rest of today and then the start of Thursday's lecture, I'm going to talk about 2 frameworks for doing this. And they basically can be called either in terms of a position jump process, and in a position jump process, the movement occurs through jumps in position. And that's akin to that first type of random walk that we considered earlier, that we had our individuals on a one-dimensional lattice, and every tau time, every kind of tau step in time, we were making a jump right or left. And you can kind of somewhat think of that as being an instantaneous jump. So if you want a kind of an animal to kind of describe that, probably a kangaroo is your best bet for that. You're making some jump in position. So that's what we would call a position jump, and it's effectively very similar to that kind of uncorrelated random walk we were considering earlier. And then the other type of model that we're going to look at is what we call a velocity jump random walk. And in a velocity jump random walk, you make piecewise continuous movements through space, but then every so often you do a jump in velocity. Okay, so in this sort of situation, you can think about this like your kind of E. coli bacteria, that you're moving through a run and tumble. You continuously move with a particular velocity, but then every so often you do a reorientation and you choose a new velocity. So you're always moving, and we're going to assume that those kind of tumbles are pretty well instantaneous. So these are individuals that are always moving. So my kind of animal analogy for this is sharks, because, well, it's kind of common, it's commonly said that sharks need to continuously swim, otherwise they drown. Actually, that's only certain sharks that's the case, but it is true for things like great white sharks and whale sharks that they need to continuously swim, otherwise they will stop drowning. So, but anyway, we're going to consider, as I say, these two sort of ideas. Either you make a kind of a jump in space, or you make a jump in velocity. And I probably won't get through to the velocity jump random walks today. So let's kind of now look at this. And let's look at this now from the framework of a position jump run model. So let's kind of set U of x of t to be my population density of assumed independent random walkers. And we're now going to define what we call a redistribution kernel. And my redistribution kernel K is basically defines it's a probability density function to describe the for a jump taking place from position X to position Y from time t to t plus tau. Okay, so it's really just going to say the probability that you go from X to Y. So if that's the case, then we can write this down for my discrete space, discrete time process. On the left-hand side, we're going to have U of x t, t plus tau minus U of x of t is going to be the probability of jumping from, so maybe I should write that one here. We have a term on here which is describing my incoming individuals. So those are individuals that started at position Y and jumped to position X. And then we have a loss term, which is my outgoing individuals that started at position X and then moved to position Y. And in a general sort of framework, we will kind of integrate this kind of all of those incoming and outcoming individuals over some measure space, over some set dx, where dx mu y describes a measure space. Okay, so that's kind of my general position jump random walk framework. And you can set this up in a lot of different ways, pretty well according to the biological problem that you're doing it. It can describe movement in continuous space, or it could describe movement between discrete nodes, which, like in an extreme case, could just go back to my simple random walk on a 1D lattice where we jump delta right or delta left. And you can do that really by just how you just sort of set up this kind of measure space there, because this dx denotes my set of destination or incoming sites. So for example, if I allowed my jumps to be in any direction and any distance up to length r, then this set of destination or incoming sites is going to be a ball of radius r centered on x, and mu just becomes my standard best measure. If I actually allow jumps in any direction, but now actually fix the distance that you jump so that it's just delta, then at that point, the dx will just become a sphere of radius delta centered on x, and mu of y will be a surface Lebesgue measure. But if I also kind of wanted just simply to allow individuals just jump between fixed discrete nodes, then my dx would define the set of discrete positions, and mu of y would be whatever the appropriate discrete measure would be for that. In other words, this is a kind of a much more general framework that allows me to kind of describe a whole variety of different position jump random walks, where you can jump anywhere in space according to some probability, or where maybe you're still confined in a certain way. Maybe you still do a fixed length jump and so forth, or whether or not you just go to certain positions. Okay, so that's kind of my general position jump random walk. And the key modeling decision then becomes in how we choose this kernel, this k way of x and t. And that's a probability measure. So of course it should integrate to 1 basically to do so. And you could do various things with that. You can kind of introduce resting or waiting at the same time. That would be just through specifying k at the probability of jumping from x to x is just greater than 0. That would incorporate staying at the same time if you so desired. And in order to do some calculations, I'm going to kind of put this now into a slightly simpler formulation. So I'm going to assume that we can have jumps in any direction, but I'm going to fix the length of the jump, and I'm going to fix that to a distance delta. And the second thing I'm going to assume is very much like those kind of strictly local myopic random walk models that we were considering earlier, that my jump is myopic, that it's going to depend only on the information that is at the current location. So those, we're going to assume those two things there. So it's like a myopic random or strictly local random walker. So this is the sort of position that we have. If we're at position X, then after tau time, we jump a distance delta. So you can jump to any position then on the sphere of radius delta centered about the X. And you do that according to information that is centered at position X, basically. Okay, so that's going to be my slight simplification in order to kind of go through then and derive the PDE model in this case.
Excuse me, I have a quick question on this. Do we want really the integral of the second position to be 1? Because that's integrating over all the incoming into X, right?
Yes, I mean, it's a probability measure. It's a probability distribution. You're jumping every time step, basically. So you have to do a jump every time step. Yeah, so that k should integrate. So if you were at X, you have to have left X after time, after tau, basically. And
yeah, but wasn't k x y the probability to go from y to x?
Have I got that the wrong way round? So ky of x is the jump from position X to position Y, and yeah, so yeah, your incoming is going from Y to X. That's right there. And then your outgoing is going from X to Y. Yeah. Okay. So,
and the outgoing should integrate to 1, right?
Yeah. So they both should integrate to 1. Yeah.
Both.
Oh,
okay.
sorry. No. Sorry, that is the wrong way round. Sorry. Yes, that's that. Yeah. So your outgoing should integrate to 1. Yes.
Okay, that makes sense.
Sorry, and the incoming shouldn't. Yeah. Sorry about that.
Okay.
Yeah.
Thank you.
That was my. Yeah. I didn't. Yeah. So that's the wrong way round here. That should be a y of x there. Sorry about that. Yeah. So something to correct later. So let's just kind of, that should be a y, and that should be an x. Okay. Yeah. Okay. So as I say, we're going to set that up. We're going to set that up in this sort of way here to consider a strictly local myopic random walker. Okay, so if that's the case, then we've got these kind of two conditions, and we can go back to my laser pointer. Okay, so we've got now these two conditions, and we can kind of rewrite this in a slightly simpler way. So rather than that kernel, we can kind of reinterpret that kernel in terms of a directional distribution, which we're going to k of nx at t, where n is a direction, and knx at t is a directional distribution for the probability of choosing direction n on the n-dimensional sphere. Okay, so with this sort of case here, we can just sort of do a slight sort of reformulation of my model. And when you kind of do that, go through the same sort of process, you can now write your master equation in terms now, that kind of k has been replaced by this directional distribution, but essentially this is still the same sort of places. This first term here is my incoming, that you've jumped from position x minus delta n, that you've chosen delta, so you arrive at position x, and this one here is my outgoing population as well. So that's my master equation. And just to give you an illustration of how this then simplifies down, you could kind of consider two possible headings, where you just take the base vectors. So if we wanted just to have two headings, so rather than being able to go anywhere on the circle, you can either just go kind of right or left, in this case there. Then in that case there, my kind of this directional distribution would just be a sum of two Dirac delta distributions. So you either jump right or left with some probability q or 1 minus q. And that leads me back to that very first simple one-dimensional random walk on a lattice with jumps delta, basically. So it just then kind of shows how this position jump random walk is now a generalized form of that much simpler position jump random walk on a lattice that we consider to start today's lecture, basically. Okay, so you can kind of say simplify it down into simpler and simpler sort of cases. But of course, we don't want to do that. We want to kind of take this sort of general form here and work out what sort of limiting equation that we're going to do. And the way you do that is just to do exactly the same things that we did before. We just do Taylor's expansions and we simplify then the equations, and then we look at various limiting scenarios. And it becomes a little bit more complicated because, of course, now you need to consider the multivariate Taylor expansions, etc. And you kind of probably need to kind of go in and kind of study sort of different, kind of look back in textbooks of differential calculus to kind of see how those are kind of doing. But it's a kind of a fairly standard set of steps. You do a Taylor's expansions on the right-hand side. You then do a little bit of kind of tidying up, etc. Terms will nicely cancel each other out. And in particular, we're going to use this kind of, just to note that we're going to use this kind of colon notation, this double dots here, to denote this double summation here, so that this sort of second term here that you get when you go through this is effectively a summation over second derivatives of some kind of matrix A here, which in this case is this thing here. Okay. But anyway, the point is, I don't want to go into those sort of specific details at this sort of stage here. It's really, as I say, it's kind of a more complicated underlying model, but the sequence is effectively the same. You do your Taylor expansions, you tidy everything up, and then you kind of derive then some sort of equation as a result of this. And that again then has to be treated carefully in order to obtain a limiting case, because you're going to need to kind of consider about when you take a limit as you kind of send your delta and tau to 0, you need to think about the kind of the different sizes of these terms that we've got on the right-hand side here. But it's still fairly standard. You use different scalings will lead to different limits. You can consider a drift limited case there, where you take a limit where delta over tau is equal to c, and of course then in this sort of equation up there, if we assume that it's a drift dominated case there, this term will disappear, all of these terms will disappear here. You just get left with that first term there, and the resulting macroscopic equation is of the form of a drift equation, where we've now got an advection velocity, which is based on k, and in particular, that advective velocity is related to the expectation of k. That kind of integral here on the right hand side is simply the expectation of this directional distribution k. Okay, so that would be my my drift dominated limit. You can define a diffusion dominated limit as well, as say. So in this case there, you'd need to kind of assume that the size of the size of the expectation of K is effectively 0. And if that's the case, then you can take the limit as delta and tau over tends to 0 as delta squared over 2 tau is equal to D. And in this case there, as I say, we're kind of assuming that the expectation of K is 0. So that term disappears. All of these terms will disappear. And we then get effectively an anisotropic diffusion type equation in the limit there. This D is effectively a diffusion tensor matrix, which is calculated as such. And finally, you can take some sort of drift diffusion approximation. And this, of course, will be highly contingent on the size of the advection. So assuming that kind of advection is of order delta, then you can do your drift diffusion limit. And in that case, you get a combination of those two processes. Okay. But as I say, essentially, we've done the same set of steps, but now within this kind of more sophisticated framework of this kind of position jump random walk extended to higher dimensions. And this gives rise, as I say, to this kind of, it's effectively an advection diffusion type equation, but it's a little bit more sort of sophisticated than that, in particular in terms of this this diffusion type term on the right-hand side. The advection is related to the expectation of your directional distribution for choosing the direction of movement. So you get a drift in the direction of the expectation of K. And the diffusion tensor matrix, again, is based on statistical properties of your distribution K. And I should note that this is actually kind of appearing fully inside this kind of double gradient here. And that's going to have consequences then in terms of some of the macroscopic behavior that you'll get from this model, as we're going to go on to when we kind of in the final sort of lecture in this sort of course. Okay. So that's kind of our position jump random walk, and that's kind of the sort of equations that we get. And to finish then today's sort of lecture, let's just go through a couple of quick examples on this, which hopefully will show how this kind of then works in simpler cases. So if we look at a two-dimensional case, then of course in that case there, then my kind of direction can just be defined in terms of some sort of vector cos theta sine theta. And if I want to calculate my advection, then I just kind of do this integration. So I'd kind of calculate the integration of k of theta over times cos theta sine theta d theta. My diffusion tensor matrix, when I kind of do it in that case there, I want to integrate something of the right-hand side here, of what I've got in this sort of form here. And of course, whether or not you're going to be able to do this is now going to really depend on what you choose for that directional distribution. So whether or not you can obtain an explicit calculation is going to depend on whether or not these calculations are even going to be possible, basically. If you choose, there's different types of directional distribution that you can choose. So whether or not you can form explicit calculations is going to depend on those. But it can certainly be done for very, very simple cases. And a very, very simple such example would be just to choose a uniform distribution. And you can kind of work out what you're going to get in this sort of case here. Then we choose any direction is chosen with equal likelihood. So k of theta would be 1 over 2 pi. And then the calculations become very, very straightforward. The advection would just simply be 0. The diffusion tensor matrix would just come out as a kind of an isotropic diffusion type process. And my limiting equation would be just an isotropic diffusion equation. That's what you'd get in 2D. You could do the same thing also in higher dimensions as well. So an isotropic random walk, you could extend that up to n ND, you could kind of choose K to be a uniform distribution, and you can go through exactly the same calculations, and you get the limiting equation, which would be of this form, of an isotropic diffusion equation. Okay, but that's generally not going to be the case if you choose other forms for your directional distribution. And again, when we get to the next lecture, I'm going to sort of talk about some cases where we use specific directional distributions, such as the von Mises distribution, and we're going to get different types of equations when we go through this process. Okay, so that's the position jump random walk model. Just as a final note on this one there, just to kind of complete this sort of part of today's sort of talk, you can actually do the same thing that we did earlier here for this kind of more advanced model, also to kind of solve mean first passage type problems. And again, I kind of leave this again as an exercise for anybody that's interested to do. You can kind of setting this up in the same sort of way. Then you go through the same process and you get now kind of a much more complicated sort of problem to solve for your mean first passage type. But basically, you know, it's the same sort of thing. You kind of took the mean first passage time, you put it and create that kind of discrete space, discrete time master equation. You go through the kind of the expansions, etc. Then you derive the limit equation. You now get something like this. And if you wanted to do this to solve first passage time problems, you'd obviously need to kind of solve that equation under some domain with appropriate sort of boundary conditions. And there's a paper by Mackenzie et al. From 2009 that kind of does this these sort of calculations, which is for anybody interested in those sort of problems. Okay, so I think we're coming up to 4 o'clock, so I'm going to finish that for today in terms of where we're at. So we kind of got through most of what I wanted to talk about, but we've kind of left one final type of random walk model that we want to analyze, and that's this idea of a velocity jump random walk. And you can kind of think about this as being my closest to my biological movement type places. So we don't have artificial jumps in location. We now have individuals that move in continuous runs, so with a kind of a run in a particular velocity, and then make occasional turns. And in Thursday's lecture, we'll go through effectively this kind of final example of a random walk process, the velocity jump random walk, show how we can derive the macroscopic equations for that model, and then very briefly then consider how we can then apply this framework to look at some of those case study applications that I introduced in yesterday's lecture. But finish there for today and pick it up again on Thursday.